All right, so in the calculation section of this video, we're going to be looking at a question in which we determine the molar heat of solution of potassium nitrate, which means calculating the energy changes which are happening as potassium nitrate dissolves into water. Now, there are two main parts of this question. There are parts that talk about the water and the energy changes that are happening there, as well as the potassium nitrate. So the question reads, in a typical experiment, 100 grams of water is placed in the polystyrene foam cup and the initial temperature of the water is recorded as 25 degrees Celsius. 5.05 grams of potassium nitrate, KNO3, is added to the water while stirring. The temperature of the solution falls and the minimum temperature achieved is recorded as the final temperature 21.7 degrees Celsius. And we're being asked to determine the value of the molar heat of solution of potassium nitrate in kilojoules per mole. Now, what I want to talk about first is the energy changes in the water. The water is really important to this question because it's actually how we can begin to measure the energy changes which are happening. What we can see is that the temperature of the water starts at 25 degrees Celsius and ends at 21.7 degrees Celsius. Now, this really has no direct implications on the energy changes of KNO3. It's happened because the potassium nitrate has dissolved, but what we're physically measuring are changes in energy of the water. And what that means is we can determine this Q value here. It's an experimentally measured value, which is a measurement of an energy change of a substance, even if it's not the one that we're focusing on in terms of reaction. Now, in this case, Q of water is going to be negative, and we know that because there is energy being lost in this process, and that's evidence because delta T is negative as well. And what that means is that the temperature of the water is decreasing, which means it is losing energy. What we can look at as well is some information about the potassium nitrate. In this question, we're being asked to calculate delta H of solution, the energy change that the potassium nitrate has as it dissolves. Now, in this case, that energy is going to be positive. We can see that there's energy being lost from the water, which means that there is energy being gained in the potassium nitrate, and that's energy is being taken from the water, which means that we're working with an endothermic process here. Now, using some of this information, we might be able to come back and look at this towards the end and compare it to some of the calculations that we did below. So moving down to the bottom section here where our calculation is, I've already started to set up a little bit of a data column. So we're going to be using that to put all of our information in before we then go and do our calculation. Now, the first thing is that we need to determine the Q of water, the energy change in the water. At the moment, that is unknown, but we can use M, C, and delta T to find that. I'm going to start with C here. C is our molar heat capacity of water. It's 4.18 times 10 to the 3 joules per kilo per Kelvin. And then our mass of water is 100 grams, but you'll notice that because we're using the heat capacity here that has units in kilos, we need to be substituting in numbers that match those units of measurement. So I'm going to be writing that down as 0.1 kilos. Now for delta T, it's in Kelvin, but because we're taking a difference here, we don't actually have to calculate these temperatures or convert these temperatures to Kelvin, because when we take the difference of the two, essentially there is no difference. And that's because Celsius and Kelvin increase and decrease at the same rate. So a change in Celsius is the same change in Kelvin. So to find the temperature change in water, which should be negative, we need to take our final measurement and subtract our initial measurement. And that should be negative 3.3 degrees. And again, we could write that as negative 3.3 degrees Celsius or Kelvin. Because we're working with Kelvin, I'm going to write Kelvin. Then moving down, we're going to also need to do some work around the molar heat of solution. Now for that we need Q of water, which we're calculating in our green section, but we also need the number of moles of potassium nitrate which have reacted. Now to find that we need the mass of potassium nitrate, and we also need the molar mass of potassium nitrate. The mass is being given to us, that's why we're using this equation to find the number of moles. That's information that we've been given about potassium nitrate, so we can write that down straight away. That is 5.05 grams. Now we also need the molar mass for this calculation. Now to do that, we can add up the molar masses of all of the elements or the atoms present. So first off, we have potassium, which is 39.1. The nitrogen, which is 14.01, and the oxygen, which is 3 lots of 16. When you put all of that together, you end up with 101.11 grams per mole. And in a moment, we're going to be able to use that to calculate N for the molar heat of solution. So to calculate Q, we're going to do M times C times delta T. When we put that into our calculator, what we should end up with is negative 1,379.4 joules. Now note that I've given my answer in joules because it matches the heat capacity for water in its units. Same thing as we did for Kelvin essentially, and for same thing that we did for Kelvin and kilos. Now to determine the number of moles of potassium nitrate, N is equal to 5.05 grams divided by its molar mass, which was, let's drop that to have a look, 101.11. When you put that into your calculator, you should find that that is 4.99 times 10 to the negative 2 moles. Now to calculate the molar heat of solution. So that's going to be negative Q of water. So negative 1379.4. So notice that those negatives will cancel out and mean that the delta H of solution is going to end up positive, just like we predicted at the beginning. And we're going to divide that by the number of moles. So 4.99 times 10 to the negative 2 down the bottom. When we put all of that into a calculator, we should end up with 27,643. Well, that's on a 3. 643 joules. Now, we've been asked for the answer in kilojoules per mole, so we can just do a conversion the same as you would between grams and kilograms, a factor of 1,000. So if we divide by 1,000, we get 27.643 kilojoules, and these are both per mole. Now, notice, based on the data that we had at the top as well, this 100 grams here is actually only to one significant figure. We don't know if it's been rounded to the nearest 100, nearest 10, or nearest 1 gram. So we should also be taking our answer down the bottom here and reporting to one significant figure. So 3 times 10 to the 1 kilojoules per mole. And you should also notice that our answer that we gave for delta H over here is positive, as we said up the top, and the answer that we gave for Q of water was negative, which matches the theory that we talked about at the beginning. And there you have it, the molar heat of solution for potassium in kilojoules per mole to one significant figure. Thank you very much. In the next video, we're going to be looking at going further with our enthalpy concept and looking at Hess's law, which starts to explain energy changes in a chemical reaction in stages. But until then, have a good one.